So my name is Michno, and I'm from Austrian Institute of Technology, which is one of the biggest research institutes in Europe and also the biggest one in Austria. We are working on high-speed sensing, so very fast acquisition using cameras and finding some, for example, defects or monitoring some processes. We are working on inline computational imaging, so creating 2.5D and 3D images from images captured by the cameras. And also we have a lot of AI solutions for different areas of industry. This paper was created during our work on the metafactoring project, which is European Horizon project. And the project is mostly intended to create a digital twin and also some kind of framework for creating more resilient production in the welding and casting use cases. So this work was made by different partners from different countries, like from Austria, Germany, Belgium, Portugal, Slovenia. And what is the biggest problem in the casting? So in the casting, especially in the high pressure die casting use case on which we focused in this project, we have a lot of different problems. And also the quality is a big problem because it needs to be very, very precisely made, especially when we are, for example, producing for the aerospace industry or for the automotive industry. So even small defects can have a lot of impact on the part, which is then used in a car, for example. So this is very crucial. And in this process, we need to find the root cause of the different problems, on which I will tell a bit more later. And in order to detect them, we need to find them as fast as possible in order to reduce the scrap rate and reduce the number of parts which has to be tested every day. And for people who are unaware, every day we need to cut some casted parts into few smaller parts in order to check if there are no, for example, small pores inside or cracks or other things. So these parts then has to be just removed from the production and then just throw away. So this produces a lot of scrap, and this is one of the biggest problems, to find some methods for faster and easier and less time-consuming defect detection quality and other monitoring things. So how looks the whole process? The process looks like this. So we have a molten metal. In this case, we were focusing only on the aluminum. And maybe I will use laser pointer. So here we have this molten metal. And this molten metal is going through some channels to this part, which is a mold. And inside we have different shapes. So each part has different shape, and during the process, this metal comes into inside in very high pressure, and then it solidifies as the mold is getting colder. And after solidifying, the part is removed from this mold. Then there is made some kind of spraying using some lubricants for just cooling down the whole mold and also preventing from stitching these parts into the mold. So this is how looks the process. So from this animation, it looks quite simple, but yes, when we came into some details, it's very complicated process. And in this process, we can collect different types of data. So one of the types is different parameter controlled by the high pressure die casting machine, like measurements also. So we have some kind of predefined parameters and also some kind of averaged values read from the process during casting. Another type of data, which is the configured process parameters. So these types of data are just statically made before the process, and they are not changing at all during the whole casting. Then we have time series data. So during the casting, some parameters and some measurements are different. For example, the pressure can change a bit, also the temperature. So there are many things which are changing during the process, and with time series data, we can capture them in different time points. There are also, not always, but in our project we captured, there are also captured thermal images of the mold, so of these parts which are forming the part. And in this project, we captured two types of images, one before the casting, before the spraying. So when the casting is done and the part is removed, we take one picture of the mold, and then after spraying, we took another image. So just to have information how well the cooling down process was made with the spray. And also, after the whole process, there are made some quality checks made by humans, by people, by machine operators, and then we know exactly if the part is really good or not. So there are many different types of them, like, for example, MRI or X-rays, so quite time consuming. There are also some leakage tests where we put some liquid inside, and for example, if it's some kind of engine or other part which has to be without any pores, which are we are providing some leaking, then these types of tests are very useful to check if the part is really good or not. There are also different types of defects. So we have gas porosity. So during casting, some air can just go inside the part and create some small bubbles inside. There is also shrinkage porosity. So because of the of different types of solidifying and the setup which we are using is like on this animation, there are different areas of the mold which can just cool down a bit differently than the others. So this part is not always very well cooling down in the same way in all areas. So this may cause also some porosity, so also some bubbles inside because of different shrinkage regions when the part is cooling down. There are also so-called cold shots. So it occurs when, for example, the temperature of the melted metal is too low, for example, in some areas. There are also misruns. So, for example, when the metal is not going to all small details in the mold, so there are some empty spaces, and also some other defects which are a bit maybe less occurring in the process. And in this project, we focused, especially in this use case and in this paper, we focused only on the porosity. And we don't have information if it's a gas porosity or shrinkage porosity after the tests made by operators. So we treat porosity as one defect class. And when it comes to the quality control, these automated quality checks made by the machines are made. So for example, there are predefined safe margins of different parameters before the process, and then the machine is just checking if the readouts from the different sensors which are inside are correct or not in this range. If they are going outside of the safe range, then the part is already classified as a part which contains some problems. After the casting, there are also made this visual inspection and leakage tests, which are very useful for finding these porosity problems. So these are three types of quality control, which is most often done. And sometimes they also made some X-rays or other things which are not distracting the parts, but they are also time consuming. In the most severe cases, they also made some cuts of the part, which then cannot be used anymore, but then we will know what problems are inside. And what is the main motivation of our work? Our work was focusing on finding some way to decrease the number of different parts which has to be tested after the process. So to have some improved automated quality checks during the casting process. So this can be very useful for example, the factory workers, and also for the whole process and for the whole industrial area, because then we can find defects much easier and faster without any destructive tests. And even if there are still some problems, then the number of parts which has to be tested should be much lower. So also the costs are much lower. In order to provide such system, we made few things. First of all, we took these two images before and after spraying, so we check how well the mold is cooling down. Then we extract features from these images, and using features, we create some structure called fuzzy cognitive map, and using that, we are making some classification and providing results if the part is containing porosity or not. So here we have an overview of the feature extraction model, but here we have a bit simpler one. So this with more details, and here we have a bit simplified image. And what is the main core of the feature extractor is the encoder. So we trained autoencoder on training images, and then we extracted only encoder part. And also we have a trained dense network, and we concatenated these all four parts, so 2 parts per one type of image, into one network, and then we trained everything together, and as a result we got some classifications, but as a feature extractor we just removed some last layers of the network and then used the output as features. And these features are then transferred to the fuzzy cognitive map. And how it works. So during training, we have these features from the previous state. Then we are clustering the features into some number of predefined clusters. Then we calculate similarities between the features and the clusters. And from that, we are creating fuzzy sets, which then are used to create the fuzzy cognitive map, which is some kind of a graph connected with some features from the neural network. So this is something between the neural network and a graph made by human. So this is very useful data structure and architectural model. And during prediction phase, we also extract these features. We calculate similarities with the centroids, and using already made map, we are making inference process with some different types of activation functions. And as a result, we are given two results. One, if it is good part, and the second one, if it's not a good part, so containing porosity. The map looks like this. So in case of the visualization of the map, it looks very strictly like a graph with different edges, and these edges are directed to different other nodes, which are called concepts, or to the results, which are also called concepts in this way, but they are used as output of the map. And between the concepts, we can have positive and negative edges with negative or positive weights, and also concepts inside can store some kind of state. So this is a bit more complicated, like a real simple graph, even if it looks like a graph in case of visualization. And for the experiments, we used a lot of images for the training. So because we used both images for one part, and so we had more than 3,500 of samples, which is 7,370 images of class OK, so good part. And because during the process, it's not so easy if it's a real working factory. It's not easy to gather a lot of bad samples because this is not the main aim of the real production. So we have only 612 images of porosity class. Because of that, we made some additional augmentation in order to improve this number of bad class, but still, yes, the training data set was a bit imbalanced. And for the testing, we used 308 images of good parts and 204 images of porosity class. So these are quite big numbers in case of the total number of samples, but yes, we have different proportions. And for the evaluation, we use different types of metrics. We use area under the curve, accuracy, but this I will show that is not the best for measurement here. We used also Matthews correlation coefficient, balanced accuracy, and F1 scores for each classes. So why these metrics? Because we can measure different types of results in different ways, and we can, when we combine everything together, we can have some kind of holistic and complex information how well the classifier works. So F1 score was quite good because it shows the per class detail and focuses on the real accuracy of the predictions. The Matthews coefficient is also quite good for dealing with the imbalanced data sets. So this was quite good for getting the real information how the performance looks for the classifier in a bit imbalanced data set. Yes, accuracy in this case was not the best because it's good for balanced data sets, but not so well for the imbalanced ones. And also balanced accuracy and AUC are quite good for imbalanced data sets, and they measure each measurement, each metrics works a bit differently. So we can have different ways of getting information how the model is performing. So here we have the results for the neural network-based classifier. So only this part which was used for the feature extraction. So here we we checked how well only using this feature extractor will work when we are not removing the last layers. So we can see that there are some models which are working better and some which are unable to classify the whole model. So, for example, the using d.o.o was not the best. Also, even using some encoder approach, so concatenating this with encoder subtree was also not as well as others. And because for DenseNet plus encoder we got the best results, we made all experiments later with these types of network. So here we can see the confusion matrices for the results of these models. So without the fuzzy cognitive map. So you can see that, for example, for d.o.o, all samples were classified just as porosity. But for example, for DenseNet plus encoder, it worked quite well in case of comparison to other, like d.o.o. But still, there is a lot of number of very high number of the samples which were classified as, for example, okay, but they were really not okay. And here we have results for the different types of fuzzy cognitive map with extracted features. So we also measure different models, and as expected from the previous state, the best was using DenseNet plus encoder as feature extractor, and then everything was trained using these features into fuzzy cognitive map. And for this, we got 0.55 MCC and AUC 0.73. So quite high values, but still there is a lot of to do and a lot of to improve, because yes, this can be also still much higher. We got better classification. So here we see also the confusion matrices for the results. So we can see that the number of porosity detected was quite high, but still there are some samples which are not classified correctly. And this may be caused because we use only thermal images, and a lot of, as I showed before, a lot of porosity cases may be not the shrinkage porosity, but the gas porosity, which is not strictly related to the temperature of the mode. We also made some comparison with the measurements made by the machine. So with these average values just gathered during the process. And here we trained light GBM model for classification. And you can see that also we are not able to find all porosity cases. So this may lead us to another idea, to use not only one type of data, but to fuse all of them. And here we have some initial results on which we are currently working, and now we have much better results. But yes, when we were sending the paper, it was like this. So here we have some idea how it can work. So when combining both images and sensor data from these average measurements during the process, we decrease the number of porosity not detected, increase the porosity detected number, and also use okay cases. So fusing data in this use case the casting can improve the results. But in this paper, we focused only on the thermal images and only on this small area. So here we have all results combined for different types of models. And here we have only the best results. So we can see that different measurements, different metrics have different values. So for images, we have a bit lower MCC in comparison to light GBM, but it must be stated that not the same results were obtained during the tests by the light GBM, so using these average values, and by the thermal images. So then they can be just used together to overcome problems from one or other classifier. We also compared our model with another work which we found using HPGIN, so generative networks. And this work was made exactly on the same types of data as we have in the project. And we can see that on the same data, we got a bit lower MCC, but we have quite similar results for the F1 scores, and this was made by the balanced data set. And in case of imbalanced data set, the results are much better, but still this is an area which we have to improve. And now we have much better model with better architecture and more complex than we showed here. But this will be a part of the next publication in different conference. And here we have also the visualization of the results. So we can see that not always the classifier was 100% sure that the result is porosity, but still it was quite high. And for the use cases when it was not really sure, we got a bit lower probability as a result, but still it was very useful for the operators. We also made some kind of ablation study where we measured different parts of our architecture, how it performs. And for example, when we remove different types of centroids, we obtain different results of metrics. So we can see that, for example, when we reduce the number of, like here we can see, when we reduce the number of the centroids, the average accuracy and balanced accuracy AUC F1 scores for both classes and MCC is decreasing very highly. So when using 13 centroids, up to 8, still the results were quite good, but when we removed more, the results were much worse. We also checked different types of activation functions in the fuzzy cognitive map. And we can see that some of the activation functions works quite well. And the results were quite similar, but for example, for TAN-H or RELU, the results were not the best. As we can see, the MCC was equal to 0, so the classifier was not working correctly. So it's also very crucial to choose the right activation function. And yes, this slide already shown. And also this method from this paper has some limitations. So for example, because of different types of porosity, we can find only these ones which are connected to the thermal surface. So we are limited to only them. So for this shrinkage porosity type. So gas porosity may be not so easily detected. And for this, we need additional data sources, like, for example, this average value or even time series. Also, choosing the right parameters and activation functions is very important. And the number of chosen centroids and types of them, so different types of clustering, has also influence on the performance. So in this project and this paper, we introduced a new application of fuzzy cognitive map classification using image classification, which is also quite novel and new. Only few other works were focusing on that. Also, we created new feature extractor with multiple clustering methods, and this work is an ongoing work, so still the results are not as good as they can be in the future, but even now they are very useful for the machine operators. And the key advantages of our research was the faster training than, for example, GAN methods. Also very easy addition of different new data sources and new classes. It also scales very well in case of the data set size and the time of the inference. And also, yes, we might balance accuracy the best in comparison to other methods, and also the ablation study was made in this paper. So as a future research, we'll integrate our classifier in improved version into the real working manufacturing environment. We develop some kind of dashboard, which is now already done because the paper was written some time ago. And in case of the research roadmap, we will improve the classification results using a bit improved model for the feature extraction and also the fuzzy cognitive map. We test different other data sets with also additional data sources like these average values from the machine, from sensors, and we will validate the whole system in the real working production environment. And as the last part, yes, this work was funded by the European Union and the Manufacturing Project, and will be continued still until the end of this year. I would like to thank you very much for listening, and